fascination with the red planet began with astronomers in ancient Egypt. The Babylonians and Greeks tracked the motion of the planet, and Galileo made the first telescope observations of Mars. Even today, when we look into the night sky and see the pale red dot above us, it inspires us to wonder about this nearby world. The question we have now is, how do we get there?
In the harsh environment of space, maintaining a livable atmosphere can be extremely challenging. Astronauts need reliable systems to provide clean water, breathable air, and stable temperatures, all while being millions of miles away from Earth. These life support systems must work flawlessly, while still mitigating their impact on crew operations. Unfortunately, and as of today, oxygen production systems for human spaceflight are not as reliable or as efficient as we need. Just as an example, if we want to send 4 astronauts to Mars on a return trip, today it will be more mass efficient and less complicated and less expensive to just store all this oxygen in a tank instead of recycling it from the cabin atmosphere. Part of the reason is that in order to separate gases from liquids in microgravity, we need to deal with the lack of buoyancy. And this lack of buoyancy forces the adoption of a series of extremely complicated mechanisms like centrifuges, valves, pumps, or water recirculation loops. That has been the state of the art as of today. But here at Georgia Tech, we are thinking about a disruptive new architecture, magnetohydrodynamic oxygen production. The term electrolysis describes the splitting of water into hydrogen and oxygen. To electrolyze water, you just need 3 things: some electrodes, an electrolyte to make water conductive, and some power. Here you can see 2 electrodes immersed in water that has been made conductive by means of an electrolyte. When we apply a potential difference between these 2 electrodes, we are closing an electric circuit. Charged molecules are flowing from one electrode to the other, inducing a current. Well, it turns out that in the presence of a strong magnetic field produced by these neodymium magnets, which are permanent magnetic materials, we can induce a Lorentz force, a driving volume force that moves the liquid in a given direction. With some engineering, we can exploit this effect to our advantage in space to produce oxygen for human spaceflight. Theo is going to explain you how we did that.
Since our overarching goal is reliable and lightweight oxygen generation for astronauts, it's worth examining why current technologies are insufficient for the Mars mission. As Alvaro shared, separating gas from liquid can be quite a challenge when you don't have gravity to assist. The pump and rotary separator, currently employed for this on the International Space Station, are plagued with issues. Pumps degrade rapidly with near constant use, lubricating materials expire after long-term storage, and the recirculation loop pressure can be unstable. Since astronauts are dependent on this system, spare parts have to be carried for failure-prone components. And what this would mean for the Mars mission is launching 4 or even 5 replacements for each unit. Plus, replacement activities cost valuable astronaut time during the mission. What these findings show us is that we require a new architecture if recycling water is actually going to be more efficient than just carrying compressed oxygen gas. That's where our magnetohydrodynamic design comes in. You might have heard about this in The Hunt for Red October, where Sean Connery's submarine supposedly employed it for a silent engine, and while not technically feasible at that speed and scale, we can use it in our electrolyzer. So in an alkaline cell, you already have current flowing between electrodes. Those are the orange lines. Then, if you place a magnet nearby, its magnetic field, shown in green, induces a Lorentz force on the fluid, which is shown in blue. If these fields are strong enough, the swirling motion generated in the drive is enough to force the fluid to the outside wall, while the gas, hydrogen and oxygen separated by a membrane, is forced toward the inside, where it can be extracted for use by astronauts. So, you might be wondering, what would this actually look like in the real world? Here's a subscale 3D printed mock-up of the prototype I'll show in a minute. You can see slots for the magnets, plus the electrodes are separated by electrolyte and a membrane, and we have acrylic viewing ports for visualizing bubble movement. If this whole thing sounds a bit far-fetched, don't worry. The Lorentz force is well characterized in the literature, and our lab has demonstrated this functionality in microgravity drop tower tests. The fact that phase separation is accomplished without moving parts is a big deal. By eliminating the riskiest components, we dramatically simplify the fluid handling architecture. And besides additional sensing and filtering on gas outlets, plus a new buffer tank to replace potassium hydroxide, this system is relatively similar to the currently employed oxygen generation assembly on the ISS, and it would interface with a Sabatier system in order to utilize generated hydrogen and reduce net water consumption. So here's our partner, Giener Labs, to share that analysis.
Georgia Tech's Low Gravity Science and Technology Lab has partnered with Giener Labs to explore the feasibility of this technology. My name is Zach Lynn, and I'm Giener's Director of Aerospace and Defense. Giener Labs is a leader in electrochemical research and development for spaceflight applications, with over 50 years of experience in electrolyzer and fuel cell design. Giener currently manufactures several electrolyzer technologies for life support, including the electrolysis cell stack for use in the ISS Oxygen Generation Assembly, or OGA, and its replacement, the Advanced Oxygen Generation Assembly, or AOGA. The OGA electrolyzer currently deployed in the ISS uses proton exchange membrane, or PEM electrolysis, while the MOGA electrolyzer uses alkaline water electrolysis, a well-established technology that's very similar to what's used in the Russian segment of the ISS in their life support system. Alkaline electrolyzers like MOGA are inherently more resistant to most contaminants in their feed water. Power-drawn reactive utilization should be comparable to state-of-the-art PEM systems, with the only fluid losses expected during the initial startup sequence. A clear drawback to this system in its current form is the use of toxic and highly corrosive potassium hydroxide instead of deionized water. However, this challenge has been successfully managed in microgravity before by the Electron system on the ISS. The use of less harmful electrolytes can be explored. The potential benefits of the MOGA electrolyzer are evident when we consider these preliminary mass estimations for several long-duration missions. The AOGA comparison represents our estimation of what a comparable PEM system using the OGA architecture might look like for the Mars transfer mission. Simplifying the balance of plant leads to a reduction in system mass, and further improvements are seen when reliability is taken into consideration. Our initial systems analysis demonstrates that a successfully designed system using the MOGA architecture could provide a significant improvement in reliability necessary for long-duration crewed missions.
All right, so we are midway through the MHD3 assembly here. That's the Magnetohydrodynamic drive demonstrator. And so what you see is a row of magnets around the central membrane, which is in the white here. And we have a plastic case and then stainless bottom plate and stainless top plate.
So we have our circumferential array of magnets halfway filled in here, and the direction of polarization is radially inwards. Our north is pointed inwards.
All right, welcome to the test setup. Before I jump into describing the demonstrator you see here, I want to highlight that the purpose of this hardware is to validate and inform the models we're using in the optimizer, which is performing a preliminary sizing for the space system. So for example, characterizing the angular velocity from the Lorentz force as a function of the current density or the current per electrode area is a critical parameter for the drive. Understanding the thermal performance is going to play into what kind of cooling architecture will be required on the spacecraft. Humidity of output gas streams, cell evolution over time, as well as just understanding assembly, what's feasible. Things look great in CAD, and we all know that they don't always assemble the way you expect. We shrank the width of the seals between the magnets and electrodes in order to maximize the Lorentz force, but that led to some minor external leakage in the first article, hence the C-clamps you saw earlier. And in order not to break the symmetry of the magnets, we required a pretty different layout from the typical alkaline or PEM stack configuration. And finally, here's the drive operating at 500 milliamps per centimeter squared, which is at the upper end of typical non-AEM industrial alkaline current densities. You can see bubbles going both upward by buoyant forces and downward by magnetohydrodynamic swirling, with the most flow downward in the center, interestingly, probably because of the large gas flow just out of view on the left and right side of the annular electrodes. So overall, this first article has given us a ton of insight into how to design a system like this, and the testing has really only just begun.
The trip to Mars is the latest manifestation of humanity's never-ending passion for exploration and discovery. By developing reliable, efficient, lightweight life support systems, systems that we can trust millions of miles away from Earth, we are taking a leap in the right direction. We are excited here at Georgia Tech and Giner Labs to work with NASA to realize this vision.